In this video, we'll be describing the Clausius statement and the Kelvin-Planck statement of the second laws of thermodynamics. So we're going to start first with the Kelvin-Planck statement. As a little background, the Kelvin-Planck statement, half of it is named after Lord Kelvin, also known as William Thomson. He was a professor in Great Britain and was the first scientist in England to be elevated to the House of Lords. He was a pioneer in thermodynamics, studied the work of Carnot, Joule, and Clausius, and had a lot of early ideas on the second law. In 1851, he said, "It is impossible by means of inanimate material agency to derive mechanical effect from any portion of matter by cooling it below the temperature of the coldest of the surrounding objects." He was also a big proponent of a thing called lost heat, the fact that you just couldn't get some heat back. A little later on, Max Planck came around, who was a German physicist, and what he described the idea that frictional pressure, so the energy from friction, never does positive work, so we can never recapture that friction to actually do work. Well, scientists have basically lumped these two ideas together to form the Kelvin-Planck statement, which is in effect that a cycle cannot produce work with heat transfer from one thermal reservoir. So what does this mean? So if we have a diagram here, you can see our thermal reservoir up above. We have the work being produced. What this is saying is you can't just produce work with heat transfer from one thermal reservoir. All of the energy from that thermal reservoir cannot be converted into work because you're going to get some friction, you're going to get some losses. So the Kelvin-Planck statement is a way of describing the efficiency, of how efficiency relates to the second law of thermodynamics. So you can never have 100% efficiency in a real system. That would violate the second law. Another way to describe the second law is to look at the Clausius statement. So the Clausius statement is named after a German physicist and mathematician named Rudolf Clausius. And he saw a contradiction between Carnot's principle, which was looking at how energy transfers into heat, and the balancing, the conservation of energy. He was noticing that it wasn't balancing. So in 1854, he published a paper in which he wrote that heat can't go from a low temperature reservoir to a high temperature reservoir without work input. So this may seem kind of like common sense to you if you think about it. So if you go out into the cold, say it's wintertime around the academy, and you decide to go outside, just standing out in the cold, if the temperature outside is colder than your body temperature, heat is not going to come to you. You're not going to get warmed up standing out in the cold. If anything, the heat is going to go the opposite direction. Without some sort of work to force the heat transfer to go in a certain direction, it will naturally go from the hot temperature to the low. Similarly, if you go out into the desert and it's 100 degrees out, you are not going to just naturally be cooled. Heat will not naturally leave your body to go to a higher temperature. Okay, so heat will not naturally go from a low to a high without some work being input into the system. So this is a way of describing the second law in terms of direction. Okay. So these two statements, that heat transfer cannot be converted to work without losses, and that heat flows spontaneously from a high temperature to low temperature, are two ways we can describe the second law of thermodynamics. The second law is really used by us to tell if a process is possible. So it's how you evaluate a process to say, could this really happen in real life? So if it violates the second law, if the heat is going the opposite direction, then you can say that, okay, that's just not. You can come up with a theory and say, hey, this balances by conservation of energy, but in reality, it cannot happen.